So let me thank the organizers for inviting me to this wonderful place. I've been to Paris several times before, but not here. So I'm delighted to be at this interesting location. So I want to tell you a little bit about kind of a unified point of view at Dirac fermions in 2+1 dimensions. And what can this maybe teach us about the Gross-Neveu model that has been around for a very long time, but maybe we don't know really everything about it. So this is the work that I've done over the past few years with my then graduate student Subrata Mandal, who is at Stuttgart now, and my present postdoc Sangun Han, who is on his way to Stony Brook in September. Mostly explained in these papers, especially the paper in the red I think will be relevant for this talk. So without much ado, I'll use graphene as kind of a working horse for two-dimensional fermions, Dirac fermions. But as you will probably appreciate, the story is much more general. Essentially, any spinful electrons which give rise to Dirac fermions essentially lead to the same algebraic structure that arises. So maybe just to remind some of you, in graphene we have two sublattices, and this gives rise at half-filling to Dirac fermions. In other words, there are two sublattices, triangular sublattices, basically superimposed on a honeycomb lattice, basically one sheet of graphite, as you know. And that gives rise to, of course, two inequivalent Dirac points, as probably everybody knows. And then you can combine these, let's say, fermions with spin 1/2, or without spin, if you like to think about the toy model, into essentially four-component fermion, combining U and V, let's say, operators that create particles on two sublattices, and those at one, let's say, Dirac point, let me call it K, and another one at minus K, right? So anyway, as probably all of you know, one ends up with one four-component fermion without spin and two four-component fermion with spin. And one point that I want to make, which is fairly, I think, well appreciated, is that you can always form these Dirac fermions so that your Dirac Hamiltonian has this absolutely the simplest form, where you basically have a 4 times the repetition of the Weil Hamiltonian, two-dimensional Weil Hamiltonian, which is just 2 by 2. So altogether, this is 8 by 8, 4 times 2, and this 8 arises basically from having two sublattices, which are absolutely essential to actually get this Dirac structure, having two Dirac points, as dictated by Nielsen-Ninomiya theorem in presence of time reversal. And if you have actually spin, as you really do in condensed matter, of course, two spin components. So this number 8, of course, is the same 8 as in the title of my talk, but it's actually not really the same. The meaning of it is not the same as in my title. So we'll come to that real number 8 in a moment. Anyway, so this is a simple construction. So essentially, I think it's better to think about graphene or anything else in 2 dimensions which has spin, which can always be put into this form by unitary transformation, as basically 4 copies of the Weil Hamiltonian, right? It's better to, I think about it that way than in terms of Dirac. It is a trivial observation, but it will lead to some interesting further observations. So of course, when we truncate the lattice Hamiltonian, we often end up with much more symmetry than what we had on the lattice, naturally. So let me just review some of the symmetries that will play a role. Of course, there is gauge U1, the number symmetry, which is, of course, exact even on the lattice. Time reversal, which has a particularly pleasing form in this particular representation, which, of course, is also exact but discrete and anti-unitary, of course. We have Lorentz symmetry, which is, of course, what makes theorists interested in graphene. Basically non-unitary symmetry, emergent. Of course, it's not there on the lattice, naturally, right, where you have just some kind of lattice symmetry. Right, so this is emergent at low energies. It will be violated already by a first higher order term in the expansion in the momentum around the Dirac point. And the symmetry that I will actually be focused on in this talk, which is the SU4, or even actually U4 altogether, internal symmetry that has to do with simply rotations in this, if you like, 4-component space, but that was in the first, sorry, oops, this goes the other way. In the first factor here, right? So because I have a unity here, right, I can rotate in that space freely. Where is that? Right here, right? So that's some unitary U. So what is this unitary symmetry, right? Obviously, it's at the level of the truncated theory. But what it consists of course, is the spin SU2, which is, of course, exact, or even on a lattice, and the emergent part, which is the Dirac SU2, right? So it seems that if you have Dirac fermions, you can just rotate between the two Dirac points, just like it's another spin, really, right? So these, of course, altogether give you SO4, but at the level of this quadratic action, in fact, you cannot avoid but having SU4. So this SU4, that emerges, of course, in any representation, but it's not so maybe easy to discern, is well known, right? Is well known, and I think well appreciated and well exploited, of course, in the physics of graphene, for example, and other systems as well. And immediately gives you a way to classify, for example, the leading order parameters, or if you like, the masses, the Lorentz invariant order parameters that would break some of these symmetries. So let me just show you that, in fact, in terms of this SU4, there are actually 3 different masses, right? Of course, if you count really how many masses you can add to this 8-dimensional Hamiltonian, there are actually 36 of them. There's this infamous number, right, 36. But in fact, they fall into 3 representations of this SU4. First one, the simplest one in this sense, is the most famous one probably, due to Haldane, that is actually a singlet under this U4. If you like, if I lamp this number symmetry together with the SU4, it's actually U4. So this is a singlet under U4. Right? It's basically just the unit matrix in its first vector space, right? And that's, of course, what actually Haldane wrote on the lattice to show that there is a quantum anomalous Hall state without any external magnetic field. This breaks time reversal, for example. And that precisely is responsible for the anomalous Hall. So the other 2, for example, are various superconducting masses, gapped superconductors, which you would write as a bilinear that breaks U1, the number symmetry, right? And since this matrix in between has to be antisymmetric, and in order for this to be a Lorentz singlet, actually this has to be sigma 2 here, because sigma 2 is actually a singlet under Lorentz group, which is SU2 in this language, right? This S that is remaining here in the first vector space then has to be a symmetric complex matrix. And therefore, this transforms under this U4 as a symmetric tensor, right? So there is a representation 10, that's basically the dimension of the representation, and 10 star, and all the superconducting masses which act as a Dirac mass basically fall into this group.
What do you mean by a mass? Because you say mass and then...
Yeah, okay.
Yeah, what do you mean when they say these are gapped superconductors? What are gapped superconductors?
Yes, excellent. So you see, if I would add a term like this by hand, then the actual Dirac fermions would have a mass, and it would be a Lorentz invariant, of course, term. And in this representation, it would look like this. Right? So if I would put it by hand, it would gap out the fermions. Of course, we don't want to put it by hand. We want it to arise from some interaction spontaneously. But you can say, OK, let me not put anything. Just look at this bilinear.
What arises spontaneously?
Let me answer that question in 3 minutes. Interactions can break these symmetries spontaneously. If it's not this term which appeared, some wave will appear. We'll come to that. Yes, if you allow me, we'll come to that. Okay. Anyway, I'm just making an algebraic statement so far. If you look at this bilinear, right, under the symmetry of U4, this bilinear actually involves a symmetric matrix here and transforms as representation 10. So let me not make any dynamical statement at this point. It's algebraic statement. Furthermore, okay, so these would violate U1, particle number U1, right? So if the expectation value of this bilinear, to be more precise, would be finite, we would be talking about one of many superconducting states that were discussed previously in literature, including the S wave that I actually didn't write here. Furthermore, you can imagine other bilinears that do not violate particle number U1, right? That have psi dagger psi here. They would have any Hermitian matrix in this vector space, right? And that would, of course, be the adjoint representation of SU4, 15-dimensional. So all of the insulating states that were talked about would basically fall into this one, including even the topologically non-trivial one, like quantum spin Hall. They would all basically belong to the same representation. So this bilinear transforms as a representation 15, if you will, adjoint representation. So this is just algebraic facts, right, about bilinears. Nothing more at this point. So let me immediately tell you what I would mean by grand unification in this business. In fact, as probably some of you know very well, even better than me, there is hidden symmetry in the Hamiltonian that I just wrote, the same one. In fact, O8 is the symmetry, not U4. And the effect of this is that if you look at all of these masses, in fact, almost all of them get unified into the same representation of this O8, except the quantum anomalous hole, which is still a singlet under O8. All of these others, now there's 35 of them for the spinful Hamiltonian, or 9 for the spinless Hamiltonian, would actually transform as a symmetric second-rank traceless tensor. So I'll write this explicitly in a second. Right. But this is
sorry. This is the infrared symmetry, or it's
an infrared symmetry. Yes, it is emergent.
Yeah, it's
infrared. Yes, that's right. There's on the lattice, of course, there isn't such thing. Only in the infrared limit. So that's the statement. So let me just work a little bit towards it. Let me just try to convince you, first of all, why is Dirac-Lagrangian O8 symmetric, and not just U4, which you could see with your own eyes just a second ago. It is essentially because we are working in less than 3 dimensions, spatial 3 dimensions. So 2 plus 1 in less than 3 plus 1. And therefore, we can exploit the fact that among 3 Pauli matrices, there is a basis in which 2 are real and 1 is imaginary. Right? So in other words, I can rotate things in the sublattice space to actually turn this sigma 2 that naturally appears when you write down almost any Dirac Hamiltonian coming from a lattice. You can rotate it into sigma 3, right? So that the whole Hamiltonian then becomes real. Right? And that you can exploit further by essentially introducing Majorana fields instead of the original Dirac fields. So after this rotation, I have some chi. I write it in terms of, if you like, real and imaginary parts. Right? And because the whole Hamiltonian now has sigma 1 and sigma 3, and nothing imaginary here among these matrices, right? In fact, chi1 and chi2 are completely decoupled. So I can stack them on top of each other into some new real field, if you will. Yeah, this one here, which now will have, of course, the same number of total number of components, 16, but Majorana reals. And the effect of this, because they are decoupled, will be to enlarge the dimension of this matrix in front. Right? From unit matrix, which was, let's say, 4-dimensional into 8-dimensional unit matrix. So therefore, in other words, if you want to be fancy, you can say that this is possible because Pauli matrices are such that you can do this. Of course, that's a trivial statement. Kind of more sophisticated version of this statement would be to say that this is possible because in dimension 2 plus 1, you can actually have the Weil condition and Majorana condition simultaneously satisfied. This is, of course, true in 1 plus 1 as well, right? But also in some higher dimensions. This is basically a property of Clifford algebra that combines the dimension of the minimal representation of Clifford algebra in a certain dimension with its reality properties. So this is, of course, famously possible also in 9 plus 1 and 10 plus 1. This is exactly why supersymmetry is usually formulated in these dimensions. So these are all algebraic statements that are more or less trivial.
Sorry, in 2 plus 1, you meant just Majorana, right?
Yeah, sorry.
In 2 plus 1, you mean just Majorana from, or not Weil Majorana?
Weil Majorana.
But Weil only makes sense in even number dimensions.
In other words, by Weil I mean just the minimal representation of the Clifford algebra in that dimension, which is 2 in 2 spatial dimensions.
Okay, so it's usually called just Majorana.
It depends what you mean by usually. Right? If you look at the supergravity books, this is exactly how they call it. Right?
They only use Weil in
okay. You can call it any way you like, right? So the fact is that you have 2 real matrices among 3 Pauli. That's all. But this does generalize to other. We can discuss this if you like later. But it's just basically terminology. So let me see. Okay, so I said this. Yeah. So if you do this unification, then what you end up with is a general mass term that looks like this. Now all of them look the same in terms of these Majorana fermions, right? And a matrix here is now symmetric real matrix in order to preserve Majorana condition, and therefore under, let's say, O8 or O4 without spin transforms like this. And that has a certain number of components with spin or without spin. So to actually come to my point, I have a short talk, so maybe I'll maybe skip some things. So what I want to discuss here, of course, is not just these algebraic statements, which are more or less trivial, but to ask a question: what happens if I want to have some interactions which also obey this large symmetry? What is the interacting term? So you can ask yourself that, and then you can show that Firth's identities allow you basically only one independent interaction term that would obey this O8 symmetry. If you want to have U4, there are actually two. But O8, there is only one. But that one can be written different ways. So let me write it in a standard way, right, which is basically the scalar bilinear squared. So this is a quartic contact term. I also want it to be Lorentz symmetric, right, and now O4. So this is one way to write it. And if you write it this way, you immediately see that this is just a Gross-Neveu model, right? So Gross-Neveu model, if you like, is really the only theory that has this O4 symmetry, or O8, sorry, depending whether you have spin or not. So that comes to the main story of mine. So what happens in the Gross-Neveu? We know a lot about Gross-Neveu, of course, but I would claim that there are some things that maybe we don't know. So what we know for sure is that if this interaction is, let's say, in my convention, maybe your convention is different, but in my convention negative, then what we know is that this thing that is being squared here picks up an expectation value. In the context that I was just explaining, this would be quantum anomalous whole. This is a transition in which, I have it also here on the board, right? Let's say on this side, which preserves this O8 symmetry. Nothing happens to O8. Inversion is actually broken. There is additional Ising Z2 symmetry that gets broken. And also time reversal actually turns out also needs to be broken. And that's the standard Gross-Neveu transition. Exactly because O2n is a spectator symmetry, we have a large n expansion for this, right? Because it basically just allows you to introduce a small parameter. And this is, of course, described in many books and works since 1974. In 1+1, in 2+1 by Gracie, and recently has been also subject of the Bootstrap program. I like this very much, this paper on Gross-Neveu archipelago.
Is this condensate derived at large n, or is this supposed to work at all n?
This is supposed to work at all n. At large n, we know exponents reasonably well as well. And we also believe we know them reasonably well even at smaller n from numerics and other methods. Large n is not the only method. So here's my main point. Gross-Neveu interaction, which is maybe better written in terms of Majoranas like this, basically looks the same way in terms of Majoranas, except that, of course, this is a larger matrix, can be written in different ways. Okay? So, for example, obviously, it's a scalar under On, so you can imagine that you can write it, for example, by using these traceless symmetric matrices that basically transform also as the irreducible representation under On. If I have a bilinear like this, for example, and sum over this index, which would go from 1 to 35, right? This is also evidently, if you think about it long enough, a scalar under O8. Since there is only one interaction, this has to be related to the original interaction. And when you work out how this is related, there is a constant in front, which has this n, and also has an overall minus sign. Now, this is, I would say, one new ingredient in this story. Now, why is this possibly important? Well, because of this change of sign, primarily. That suggests that if you are on the, what I called it provocatively, at least I tried to be, in my title, the dark side of the Gross-Neveu model, where presumably nothing is going on, there is no symmetry breaking whatsoever, suggests that there is some other GC2, at least at the mean field level. You can easily show this. There is some other GC2, which, however, is order 1, so therefore it's a little bit beyond 1 over n, where some of these other bilinears would pick up an expectation value. In other words, something like this would develop. Right?
How is this related to the old bilinear?
They are the same, except for the minus sign. See, the bilinear, sorry, it is not related. It is not related. It's a component of a symmetric tensor, whereas the old bilinear was a singlet. So they're unrelated representations.
Excuse me. if you do something like 2 plus epsilon, does that give you both fixed points?
No. Excellent question. That's exactly what I meant. So, so this I'm claiming based on basically energetics. Mean field theory would give you equally this transition, where the O2n or SO2n would be broken down into SO4 cross SO4, if you like. But on the other side, if you do epsilon expansion, which is 2 plus epsilon or large n, you don't see this at all. In other words, you don't see this other point. Which brings me exactly to the problem that I want to discuss finally. Is this mean field correct or totally incorrect? Is there anything correct in it? Is there any small parameter that we can actually discern here? Is it really possible that the Gross-Neveu model has additional transition on the other side, right? That somehow was not noticed before. Can one check this on a lattice, for example, on some kind of lattice version? What happens at the finite chemical potential, which is an interesting question, which actually brought me to this problem long ago, but it's a separate talk. So to make a long story short, let me tell you how I think about this. We think about this basically not in terms of the original Gross-Neveu, but in terms of Gross-Neveu Yukawa version of it. This is one way to calculate Gross-Neveu exponents for the standard Gross-Neveu. That was basically proposed by Zinja-Sen. You explicitly write down the order parameter. In our case, that would be this particular bilinear, coupled through a Yukawa term to your fermions, right? And then you allow the independent phi to the 4th theory, or whatever you need to write to obey the symmetry, for that order parameter, right? So this is the strategy that works extremely well for the ordinary Gross-Neveu, precisely studied in the Archipelago paper, precisely this theory. So what would it entail here, right? So what it would require is to write down the phi to 4th theory first for the order parameter, which is a symmetric m by m tensor, let's say under some OM, right? This is not difficult to write, but you discover that if your m is larger than 3, so 4, let's say 8, which we're interested in, this allows 2 quartic terms, right? So the trace s squared is obviously invariant, so you can square that, but there is trace s to the 4th as well. So there are 2 quartic terms. Now, what we know about this is that if I forget about fermions completely and just look at this Ginzburg-Landau, let's say, and do epsilon expansion for it around, let's say, 4 dimensions, which is possible, one does not have a fixed point. I mean, one does not have a stable fixed point, I should say. In other words, if you look at just the beta functions for lambda 1 and lambda 2, forget about this, the rest, which involves alpha, which is basically related to G, to G there. What you find is that there is a feedback mechanism in these beta functions that the single trace coupling, right, this lambda 2, generates in this particular term here, lambda 1, and essentially pushes it toward negative values, which ultimately makes the theory unstable. So what you end up with is presumably a fluctuation-induced first-order transition. And this has not been terribly well studied, but it has been noticed by several people before, including this gentleman here, right, who actually did this also to the 5th order, even in epsilon, and the same phenomenon persists. So it seems that, at least for m equals a, I'm reasonably certain that, in fact, there is a fluctuation-induced first-order transition. Our theory has the fermions coupled to this, of course. So there is additional coupling, Yukawa coupling, right, that also gets into these equations. And I also generalize this, let's say, to NF fermion flavors. So the dimension of a fermion, of course, is tied to the dimension of the matrix, right? But nothing stops me from looking at more than one such fermion, right? The Gross-Neveu model would correspond to this NF being exactly equal to 1, right? I don't have that freedom in Gross-Neveu model. But in this theory, I can simply add this index. Now, I'm adding it because my claim is that if we add this index and its NF is equal to 1, that does not help enough to actually get a stable critical point. But making this NF large, generically, in all theories of this type, will produce a critical point. So in other words, the flow diagrams look something like this. So I'm at the critical Yukawa coupling at the fixed point value, to the one loop that decouples really from the rest. And I'm increasing the Yukawa coupling this way. So at 0 Yukawa coupling, we have these runaway flows that I was talking about. You see, everything flows left of this green line here, which is the stability region. Right of this, the theory is stable. Left of this, you basically have to include the 6th order term. And generically, you end up with a first order transition, I believe. as you crank up this number of fermions that you introduced basically by hand, at some point there is a fixed point being born here, unfortunately in the unstable region at first. Of course, they always come in pairs. This comes from the complex plane, just what we discussed yesterday. It's a very generic phenomenon. They come from the complex plane, become completely real, and basically they get pushed, one to the left, one to the right. The stable one eventually comes into the stable region at some critical number of these fermions that I called NC2. Now we can calculate this NC2 in the epsilon expansion, for example, and we find it to be very large with some epsilon corrections. Right? So ultimately, the way this happens for large NF and does not happen, for example, for large size of the matrix is because simply there is no large M expansion. You make the size of the matrix larger and larger. This does not help. This actually can be rescaled out from the equations. And this is really tied to the tensor nature of the order parameter. So there is no large size of the matrix limit that would lead to the critical point. You need an extra parameter. So my small parameter really is 1 over the number of fermions. But that does help. And as far as we could tell, this happens in other tensor theories, for example, tensors under UN, or symplectic group, and so on. This is a very generic mechanism. And the reason why this works is that Yukawa coupling at a large number of fermions is 1 over NF. That basically generates the single trace coupling, which is also 1 over NF. But the problematic lambda 1 coupling, which is the double trace coupling, the one that runs away and causes the fluctuation-induced transition, if you have large NF, becomes parametrically smaller than the other two. Right? So you somehow demote this previously important coupling into something unimportant. It becomes small and real, and you end up with a fixed point. This is a very generic thing that happens with introduction of a number of fermions into these flavors of fermions in these theories, we believe. So basically, we end up with this region of universality where we do have attractive fixed point, this blue region, but only above certain line. So there are actually two lines because the point becomes, the fixed point becomes basically first born in the unstable region. I'm not sure that's actually a real feature or just an artifact of the epsilon expansion. But anyway, so basically the statement is that at large NF, you always are bound to have this blue region. As you lower NF at any n, you get into the region where you have just runaway flows. If you now compare this with the Gross-Neveu model, you find that the Gross-Neveu point is actually reasonably far from this line. And you also learn that if you just increase the size of the matrix, you're also getting away from this line. You're basically increasing the size of the first order transition. So the question for the Gross-Neveu model is this NC2 indeed so high, or can it be maybe lower? And that's one of these questions that are really hard to answer in all sorts of theories where such questions arise. And I think I'm doing reasonably well on time. So let me just summarize the story. So one part of the story was just simple algebra, right? Apart from terminology, this boils down to basically the fact that all these order parameters that, in a sense, play a role of a Dirac mass. In other words, if they get generated or put by hand, you would just have a relativistic mass in the Dirac Hamiltonian. They all can be organized into a representation of the group, let's say, O8 for the spinful fermions. This is a very generic feature, applies even to D-wave superconductors where these fermions arise for entirely different reasons. But as long as their number is basically what it needs to be, this is the relevant to the O8. So they become a symmetric second-rank irreducible tensor, and one is special. That's the quantum anomalous Hall that breaks time reversal, or some non-unitary symmetry that is actually a singlet under this ON. Right? So of course, the symmetric interacting theory is not new. It's just Gross-Neveu model. It cannot be anything else, in fact. And of course, about Gross-Neveu model, we have the old story at negative G. We have O2N preserving transition where actually another symmetry parity gets broken. That's the well-studied and probably the simplest fermionic critical point. Right? We don't have any Fermi surface, we just have Dirac point. And that's really the minimal interacting fermionic theory, maximally symmetric as well. So my story was that based on this Firth's rewriting of the same Gross-Neveu term, one would think that there should be another transition on what I call the dark side, right? Positive G, where certainly I don't have anything like this, but I have one of these competing order parameters that transform as a tensor under O2n, right? Different representation, and therefore a particular symmetry breaking of O8. Of course, O8 can be broken in many different ways, right? One can work out at the mean field level at least, and at the level of field theory, that this is the preferred way. This is also, for example, responsible when O8 breaks into O4 cross O4. This is responsible for having 5 anti-commuting mass matrices as well, and therefore SO5 in some kind of a broken symmetry phase. Right? So these numbers are related to this 5 from yesterday as well. So the question is really, can this transition possibly be continuous? Or in other words, if I would really somehow obtain the beta function for the Gross-Neveu model, would I, let's say, if I would do better than 2 plus epsilon expansion or large n, would I be able to detect some other 0 previously undetected? I personally think this is unlikely, but not impossible. And we see that it is unlikely because we see how hard one has to work in the equivalent formulation of the problem, Gross-Neveu Yukawa, where you find that transition indeed can be continuous, but only at the cost of artificially introducing a large number of fermion flavors, right? Which is just pinned to 1 in the actual Gross-Neveu model. But of course, you can introduce a different number, and you see that in fact it's difficult to bring that number all the way down to 1, at least within the epsilon expansion. So now we have actually the two-loop result for the correction to this leading order number in the epsilon expansion. It reduces it, actually by something like 30%. We also think that we have the second term here as well, which unfortunately pushes it again in the other direction than you would like. So anyway, so one reason why I'm telling you all of this is that I think this is actually a problem that, in principle, at least I know how difficult it is. One can study by, conformal bootstrap, at least by introducing these fermion flavors, guaranteed essentially to have a region where there is indeed a critical point, right? So one can look at the islands, see what basically happens to them as you reduce this NF, and that probably will be better than simply doing epsilon expansion, which has a very poor convergence properties anyway, right? And basically just give you some kind of a very, very vague indication of what may be happening. But certainly it's not, I think, accurate very much quantitatively. So I hope this could be a new island in the Gross-Neveu Yukawa archipelago, but I think there are more important islands to explore, of course, before this one. One, of course, being the actual Gross-Neveu Yukawa theory relevant for the Hubbard model, right, which is also not of the type that has been studied. It has actually SO3 symmetry broken down to SO2. That is a modification of the Gross-Neveu, and we all believe it's basically directly relevant to the actual criticality in the Hubbard model on honeycomb lattice. But maybe once we sort that out one beautiful day, one can also look at this, one can revisit Gross-Neveu model. So at this point, I'll stop and thank you. I'm a little bit over time. Thank you.
Thanks, Igor. I want to make sure we have time for Subir's talk, but if there are any, maybe some very burning questions. Yes.
I guess the model with NF bigger than 1 actually has a larger symmetry?
Yes. Yes, it's basically O NF cross the original orbit. That's right. So it's not O NF times 8. That wouldn't do trick. But it's O NF cross O8. That's right. That's right. That's right. That seems to be the cost. Maybe there is some other trick.
And then maybe we'll move to the next slide. Yes.
Exactly.
Yeah. So in the discussion of Gross-Neveu Yukawa model, you introduced a notation M, which is a matrix size or something.
Yes, yes, yes.
So M is actually 2n in this context?
Yes, M is 2n. That's right. So if you just have some matrix which is M by M, it would be 2n in the initial notation. It would be 8, for example, or 4 if you don't allow spin. If it's 3, for example, then the theory is actually not difficult, because it turns out, I should maybe mention, that if M is 3, which is not relevant for us, because there is no this Nielsen-Inomiya doubling, but if you make it to be 3, then these two terms are actually the same. And you end up with just Wilson-Fisher ONS theory. Right? So it has to be larger than 3 for this to be non-trivial.
Thank you. All right, let's thank Igor again.
Thank you.